This lesson is on linear, quadratic, and exponential models. So throughout this year, we've learned about lots of different types of relationships. We've learned about linear relationships, which forms a linear line. The first example is shown here for you. We've learned about quadratic relationships, and remember, quadratic relationships create a curve when you're plotting points, like the second example. And then our third type of relationship, which we're currently learning about, are exponentials, relationships that form a curve. So each of these tables and graphs show and represent all the different tables and functions graphed throughout this year. So in this section, you are going to have to determine what type of relationship an example is showing. Is it linear, quadratic, or exponential? As you know, there's different types of formulas, functions, that relate with each of these relationships. So with linear, remember the form here is y equals mx plus b. For quadratic, the function is y equals ax squared plus bx plus c. And exponential is y equals a times b raised to the x power. Let's look at some examples here of what you're going to see in this section. So the first example, it says graph the data set, and then you have to determine which kind of model best describes the data. So we're going to graph the time in bacteria here. And when we graph this, time is going to be representing your x, bacteria is representing your y, and here's the graph that represents that. So you'll notice we have a curve. At 0, it's going to be 24. Notice they go pretty high up in the bacteria. So notice how they graphed the y-axis here. Since this creates a curve, this is going to represent an exponential graph right here. In the notes, you need to make sure you're graphing the table, you're creating the graph itself, and writing the answer. For example number 2, here again very similarly, it says graph the data based on this chart and then which kind of model best describes this data. So we have number of boxes and then how many reams of paper based on the number of boxes we have. So when I graph this, boxes is representing my x-axis, ream of paper is representing my y. Notice they counted the x-axis going by 6s, and then they went up by 60s here along the y-axis. So this here is creating a linear function, a linear graph based on the data, and when we graphed it, that's what it comes out to be. Example 3. Here we have, here they're not giving us a specific situation, they're just giving us x and y. So we are going to graph. Notice we're working with decimals for y, and automatically just working with these decimals with y, that kind of tells us that's going to be exponential. Remember I mentioned in class that when you're working with decimals, kind of I at the best, you kind of on the coordinate grid, it's not going to be exact. And so you'll notice the type of graph this creates, and this is going to create a curve, which is an exponential type of function relationship taking place. Another type of examples you might see is they might give you a table or chart, and they want you to recognize the pattern taking place to help determine which kind of model best describes the data. So in the example A, it says the height of a golf ball. So with the number of seconds, the height that it's going to reach. So notice that my x values are increasing by a constant of +1. And then for my y, we're going to find the first difference. So from 4 to 68, it gives me 64. From 68 to 100, that's 32 plus 32. From 100 to 100, that's going to be 0. And then from 100 to 68, that's a -32. So if we find our second difference, how do we get from 64 to 32? That's subtracting 32. From 32 to 0, again, that's subtracting 32. And from 0 to negative 32, that's subtracting 32. So we have a constant within our second difference, which is a value of negative 32. So remember the relationship that we talked about dealing with the second difference is your quadratic. So this data appears to be quadratic right here. If we look at the second table, this is the money in CDs. So we have our X representing the time in years, and then our Y is representing our amount of money. So in 0 years, it's going to be $1,000. And then it goes up. So our X values increase by 1. And then what they did is they found a common ratio, and the common ratio of my amount in money is multiplied by 1.17. And when you have a common ratio, when you're multiplying by the constant value, that is going to represent an exponential graph. So for B here, this data appears to be exponential. With example 5, they might give you a set of ordered pairs. Here they have the ordered pairs, and they want you to look at the pattern to determine which kind of model best describes this data. So my recommendation is when they just give you ordered pairs like they did here in example 5 is to create a table based on that. So notice we have our X values representing our data, -2, -1, 0, 1, and 2. All of my X's here, -2, -1, 0, 1, and 2. And then my data, 2, is representing my Y's, 10, 1, -2, 1, and 10. So we'll see if there's a constant within my X values, which there is. We're adding 1. Then we're going to look and see what kind of pattern's taking place with my Y values. So from 10 to 1, that's -9. 1 to -2, that's -3. -2 to 1, that's +3. And 1 to 10 is +9. So there's not a constant within the first difference, but then we can look at our second difference to see if there is a constant. So -9 to -3, that's a +6. -3 to +3 is a +6. And +3 to +9 is a +6. So there is a constant taking place here within the second difference. So this type of situation is going to be quadratic. So this is all you're really doing in this section, is determining what type of function relationship is taking place based on the data and using these different methods and functions we've worked with to figure this out.